Hello, Honors Chemistry, and welcome to Chapter 11, the Ideal Gas Law. So, first of all, make sure you know all the parts, right? So obviously, let's define R first. R is the what? Right, the gas constant, and it is the thing that's going to define everything else, right? So actually, if we think about it first, what really happens is we have PV over NT is equal to a constant, right? Because P times V, right? So P times V is what? Right, this is our, right, Boyle's law, right? And then we have Avogadro's law, we have Charles' law. So basically, this is just all the laws put together, right? And we know that they're going to equal this constant value, right? That's what this is, right? So this relates all those pieces of information together, right? It's called the gas constant, 0.0821. And you do need to have the units all the time because we use units all the time. Liters times atmospheres over moles times Kelvin, right? So kind of like when we used C equals lambda nu in the previous chapter, here, because the gas constant has defined units, that's going to define the unit that everything else has to be in, right? Which means that temperature always needs to be in Kelvin. That means N always needs to be in moles, which may not seem like much of an issue, but sometimes information is presented in millimoles or micromoles or something, right? But it has to be in plain old moles, right? Volume must be in liters and pressure must be in atmospheres, right? In order for this equation to work. Yes? Make sense? All right, so if we were to do a little bit of practice, here we have an 8.5 liter tire, which is a volume, is filled with this much of a gas, which is N, with a temp of this, which is T, and I would like to know the pressure, right? So here, if we look at this, what we should notice is that this question presents no information about change, right? It says we have this volume, we have this moles, we have this temp. What is the other piece of information, right? So this is different and unique because there are no ones and twos, right? In the previous section, all those other gas laws were about change. We had a set of variables, something stayed constant while we changed something, right? Here, no change, and that's your clue that now we're talking about the ideal gas law and not one of those change-based gas laws, okay? So we would just set this up as PV equals nRT and plug in our pieces. So P times 8.5 liters is equal to 0.55 moles times 0.0821 liters ATMs times mole Kelvin times 305 Kelvin, right? And then we would solve for P. Note that this is another one of those scenarios where you are prone to dividing or multiplying at the wrong times. Go ahead and isolate your variable before you plug in all your numbers, and you're more likely to do it right. Okay, so how much volume, so this is my question, does this many moles, which is N, gas occupy when its pressure is this, and T is this, right? So again, no reference to change, we're just looking for that last piece of information. So we would just use, ding, 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 the ideal gas law, right? So P is 715 millimeters of mercury, and as you write that, you would think to yourself, oh, that's right. So you would go ahead and convert that, 760 millimeters of mercury is equal to 1 atmosphere, right? So P times V is equal to N times R times T, which is 58 plus 273, right, Kelvin, and then we would solve for our V, yes? Okay, so the next problem says find the pressure in millimeters of mercury, right, so pressure is our question, and we are given 1.133 grams of helium. What do we do with that? Right, do you have the skills to turn mass into moles? Absolutely, right, so it is a slightly more thoughtful presentation, but that is moles, right? In a 32 degrees container, which is our T, and 648 mils, which is our V, right? So we know that P times my volume, which is 648 mils, which is 0.648 liters, is equal to N, which is 0.133 grams of helium, times 4 grams per 1 mole of helium, times 0.0821 times 32 plus 273.15 Kelvin. Yes? All right, and then we would solve for P. Okay, then that brings us to, your book goes into the concept of incorporating molar mass into our PV equals nRT, right? So if we think about what we just did, right, we know that I can go from, how do we want to write this? Moles, right? I can solve for moles, right? I can take grams times, right, 1 over molar mass. Yes? So if we look back here, right, I have my grams, right, times 1 over molar mass, right? Because molar mass is technically the number of grams equal to 1 mole. But if I have to flip it, it's 1 over molar mass. Yes? Does that make sense? Right? So technically, moles are equal to grams times 1 over molar mass, or grams over molar mass, right? So if I think about that, if N is equal to grams over molar mass, right, and I were to take that and plug that in up here, right, well, plug that into here, and I do some substitutions, I end up here, right? So PV is equal to grams over molar mass times R times T, right? And then if I bring molar mass over here, right, I have molar mass times V times P is equal to grams times R times T. And then if I divide by VP, right, grams over volume is, right, that's my density term. Yes, does that make sense? All right, so anyway, that's how we get from PV equals nRT to molar mass equals DRT over P. You're not required to be able to do that, but I feel like you should. Okay. Either way, this equation does need to get committed to memory in addition to this one. So if we think about a problem, right, so this says we have a sample of gas and it has a mass of this, and it has a volume of this, and a T of this, and a P of this, and I would like to find its molar mass, right? So then you would think to yourself, okay, and actually there are two. You could just as well, for most problems, use either gas law, right? 9 times out of 10, either of these ideal gas law versions will get the job done, okay? Just depends, I guess, on how you perceive the information. Every once in a while, though, it does matter. Okay, so sample of a gas has a mass of that. Let's say we wanted to employ that molar mass equation, right? Because I would like to find molar mass, so that makes this one really convenient, right? So I need a density. What's density again? Right. Mass over volume, right? So if I have 0.827 grams over 0.27 liters, that is density, right? D times R times T, which is 88 plus 273.15 over P, which is 975 millimeters of mercury, 760 for every 1 ATM. Yes? And that would get us molar mass. All right. Next up, partial pressure. So if we look back at your book, right, so these are the two equations presented to you, and you are told that X is what? Right, X is the fractional composition. Now, there are two ways to interpret that, two basic ways, right, where it could be the percent, right? So it could be a percent, which obviously we would then turn into a decimal, because we always do that before we do math with our percents, right? It could also be a mole fraction. Okay, so now, not a mass fraction, just a mole fraction, right? Where this is symbolized as X, right? And so what that means is, just like every mole, like every fraction, like every percent, right? It would be the moles of A, whatever A happens to be, over our total moles, right? That's what our mole fraction of A is, which is what goes in there. Yes? Okay. So what that says is that the partial pressure of A is equal to the mole fraction of A, or the percent, right, times P total, right? Which should make sense because the part that is represented by anything is always the percent times the whole. Yes? Right? That's not actually a new equation, right? You've been doing that in one form or another for many years by now, right? We also know that the sum or the total pressure, is equal to the sum of the respective partial pressures of all the gases present, right? Because, going back to kinetic molecular theory, if they all act independently, none of them react, none of them combine, they don't condense, they don't do any of that. What that means is that if I have 10 particles of oxygen and 5 particles of nitrogen, they all fill the entire volume. Their respective pressures are based on the force and the number of collisions of those molecules with the walls of the vessel, right? So we can take the collisions of my oxygen and the collisions of my nitrogen and add them together to come up with P total, okay? All right, so to look at the practice problems, it says that we have a sample of hydrogen gas is mixed with water vapor, right? So we have gas plus gas. The mixture has a P total of 745 torr, and the water vapor has a partial pressure of 204 torr. What is the partial pressure of the hydrogen? Well, I know that P total, 745 torr, is equal to the partial pressure of water plus the partial pressure of hydrogen, yes? And I can solve for hydrogen. A diver breathing heliox with an oxygen composition of 5% wants to adjust the P total, so that way the PO2 is that, right? So this is my PA, this is my P total, and this is my fractional composition. So P total is what I'm looking for, is equal to 0.05 times, oh no, this is P total, sorry. And here is my 0.21, and I would solve for P total, yes? All right. One last note, right, about gases, right? So we just said that gas molecules all behave independently, right? So here, a couple of things to note. These are from your textbook. Here we have a reaction of zinc plus hydrochloric acid, which produces hydrogen gas, which we are collecting via water displacement, right? This is just like back at the, not the beginning of the school year, but back in chapter 7 where we did a lab where we collected hydrogen gas via water displacement, right? What happens is that, again, going back to life things that we know, water is constantly evaporating, right? So if I had this vessel initially, right, this vessel was completely full of water, right, filled to the top, right? But then, as it fills with hydrogen gas, right, slowly that water gets pushed out, right, because the point is it's open at the bottom, right? So that water gets pushed out of the opening down here, slowly, back into this vessel. And this space up here, this new, what looks like empty space, is actually the collected hydrogen gas, plus whatever amount of water vapor that evaporates at that temperature, right? And so here's that graph that shows you your temperature dictates, so at 30 degrees, right, this is the amount of water vapor present, right? And obviously as the temperature goes up, the amount of water vapor present increases, right? Which makes sense because higher temperature, more kinetic energy, more energy to escape into, more molecules have enough energy to escape into the vapor phase, right? So anyway, what this says is that here, anytime we collect a gas by water displacement, it will always be a mixture, okay? One more time. Every time we collect a gas by water displacement, it will be a mixture of produced gas plus water vapor, and we will have to employ Boyle's law to figure out what the pressure is of just the gas we're looking for. Yes? All right. Thank you for listening. Be good, and I will see you soon. Bye.